And with this, we move on to the next speaker of the day. Uh, our next speaker is Erfan, Irfan Ghiasvand, and Irfan's topic is CIC APT IIoT, a provenance-based APT attack datasets for IIoT environment. Irfan holds a master's degree in computer science from the University of New Brunswick, where his research focuses on detecting advanced persistent threat APTs in industrial IoT systems through the provenance data analysis. He's now working as a cybersecurity software developer at the Canadian Institute for Cybersecurity. As a research assistant at the institute, he collaborated with the National Research Council on advancing IoT security using artificial intelligence. His thesis introduced CIC APT IIoT datasets and developed a self-supervised learning framework for APT detection. Irfan's expertise lies in AI, cybersecurity, and industrial IoT security. Irfan, at this point, I would say the stage is all yours. Please share your presentation, and we're looking forward to see your slides.
Thank you very much, Sumit. Thanks for your introduction. So hello, everyone. I'm Erfan Ghiasvand, and today I'm going to talk about CIC APT IoT, that is a provenance-based APT attack dataset for IIoT environment. So this is the outline of my presentation. I first go through a short and brief introduction, and then we are going to go through a little bit of background on what is IIoT, what is advanced persistence or APTs, and what is provenance data. And then we are going to go through like the generation process of our dataset, CIC APT IIoT dataset, how we developed the testbed, what we use as the emulation, attack emulation plan, and how did we collect it and label the data. And finally, we're going to go through like a simple example of how you can actually use our dataset, CIC APT IoT dataset. So first of all, let's begin with the very simple question, and that is why data matters. So until now, you heard from three of my colleagues that we're talking about their respective data sets. So we know that the data and dataset, having a good data set actually really matters, especially in the field of cybersecurity. So the need for that is that we're trying to develop effective intrusion detection system or IDSs that we can have them to efficiently face the threats and the challenges that is out there for the safety of our cyber systems. So to develop those efficient and good IDSs and solutions, we need to have a very good data set that have like a representation of our system and how they work. We need to have the benign samples and malicious samples in order to be able to train and evaluate our models, our machine learning or deep learning models, and with that we can develop very good solutions. So in that field, we do have lack of some realistic data set in the field of, especially for the industrial IoT or IIoT. And another thing is that those datasets that are available are usually fail to reflect the complexity of modern APTs. So the purpose of our dataset, CIC APT IIoT dataset, is to have a dataset in an industrial IoT environment in IoT settings. We have a combination of simulated and physical IoT devices, networks, and scenarios. We do have like a simulation of an actual real-world APT threat is that we try to have as similar as possible a scenario to a real-world APT. And our dataset comprised of network data and provenance logs. I will talk about these things later, but we need to have these resources in order to be able to develop a very good machine learning solution for our first challenge. And there are various challenges in creating the dataset. One of them was how to capture data, how to simulate the real-world condition, and finally how to ensure that our data has a good quality. So. And to go to a little bit of background, well, first of all, what is IoT or Industrial Internet of Things that I'm talking about? So basically, you can call an interconnected network of sensors, instruments, and other devices that are networked together, and they have an industrial application. So we call this network an IoT or Industrial IoT. So these applications can be different things. For example, they can be used for manufacturing. They can be used for like energy management, and they can be used for transportation and logistics. The thing is, when you're using this kind of technology, industrial IoT, you can improve your efficiency. You can have automation in your work in industrial application. And basically, you're collecting a lot of data using this different sensors and different devices. So you can have data-driven decisions. And in that way, you can improve the efficiency of all of your operations. So, but the thing is, using and integrating industrial IoT comes with the various challenges. One of the challenges is that how to maintain the privacy of data that we are collecting. The other one is how to have the scalability for the industrial IoTs. And the most important challenge for us here is the security concerns. So why we do have security concerns for industrial IoT settings? The thing is, as I talked about this, as I provided some examples of industrial IoT, these things, industrial IoTs are very attractive targets for cyber attackers. Why is that? It's because they are basically always integrated into very critical infrastructure, for example, for power plants or nuclear plants. So basically, as they are integrated into critical infrastructure, attacking them and damaging them actually has high impacts overall. So some of the examples of such attacks that are called APTs are, for example, the Stuxnet and also attacks on Ukrainian power grids. So I talked about APTs or advanced persistent threats. So let's go a little bit of background on what is APT. So basically, we call it a kind of attack or kind of threat that is stealthy. And the important feature of APTs is that they try to remain undetected for an extended period of time and try to gain access, unauthorized access to the victim computer or the victim network. So we call them advanced because they usually have a full spectrum of intelligence gathering and the different type of tagging techniques under their hand. And also they are usually state sponsored. We call them persistence because they're not like DDoS attacks, that they are opportunistically seeking information and they're attacking their target over and over. But they are very specific. They have very specific objectives, and they try to maintain a low and slow approach. That's a very important thing about APTs. They are not constantly attacking their targets. They try to maintain long-term access and long-term unauthorized access to the target. So on that, the different resources report the dwell time, that is the average time that an APT campaign goes undetected. They usually report this dwell time between 70 to more than 200 days. So different researchers have different models of APTs. Basically, what happens, it has like different phases for each of the APT campaigns. So, for example, one of them is that it starts with an initial compromise of the network. Then the attackers or those that are behind these APT campaigns try to establish a foothold in the victim network or victim computer, and then they try to escalate their privileges and to have access on other resources or other devices. Then they try to have internal reconnaissance on the victim network. Then they have lateral movement, try to gain access to other devices or other networks within the general network. And after they reach the target, they try to maintain presence on the victim device, victim network. And finally, they complete their mission, whatever it is. For example, sometimes it's to exfiltrate some data, or sometimes it's to disrupt the operation of some industrial application. So another thing that we should know about before going to the dataset is the provenance data. So basically, provenance means any information or any metadata that describes the production process of an end product. That can be anything. That end product can be anything. But here, the end product is a system resources, for example, files or processes or things like that. So there is a widely accepted form to represent and to show the provenance data. It's called directed acyclic graphs or DAGs. And here you can see the W3C prov data model that is a widely accepted form of showing the provenance graphs or provenance data. There are two core concepts for provenance graph. They're called types or nodes and relation or edges. So the important thing about the provenance data that makes it very useful for our applications is that nodes here are connected based on causality relationship and not time. So What that means is that when you have a node connected to another node, it's not because that thing actually happened exactly after the first one. That means that these two have some type of causality relationship between them. And because of that, and as I told you in the last slide, as APTs happen in a long time, it's not going to be like a second after another. So this thing actually is very effective for detecting APTs. So this one is like a sample of a provenance graph, how it actually looks like. It's for a 3-hour experiment. You can see we do have a lot of nodes here. Blue nodes represent the benign activities of our network, our testbed, and the red nodes show malicious behaviors. I will talk about how we can label the nodes of the provenance graph to benign and malicious in the later slides. So here is the motivations and motivations that we have for this research, and also the research questions that we try to give answer to. So as I talked about it in the introduction, we do have a lack of comprehensive data set, especially when we are trying to study the APTs and the complexity of APTs in industrial IoTs. The other thing is that as industrial IoT is growing and we are integrating them into more and more industrial application, the threat of APTs and those type of attacks are escalating, and we're trying to have some efficient solution to help to develop an efficient solution to face this kind of threats, face these APTs. And the research question that we have is to how we can develop a comprehensive APT dataset that actually includes essential information we need to be able to somehow face APTs and face the attacks that are going to happen in IoT setting. The other one is to how we can use provenance data to like efficiently utilize those data in order to improve the detection of APTs. And finally, what are the methods that we can use to use the provenance data in order to detect and improve the detection of APTs? So let's go to the generation process of CIC APT IIoT dataset. So first one, this is an overview of our testbed. You can see our key components here. So basically, we do have a number of virtual components and a number of physical components. You can see that we do have a host machine that hosts all of the virtual machines that are used in this testbed. We do have two benign or victim virtual machines, VM number 1 and VM number 2, and we do have two attacker VMs that are attacking VM 1 and attacking VM number 2. So VM1 is the main component here. It is basically it's our edge gateway, and it hosts our Caldera client, and it hosts our local SCADA and works as a local SCADA and also management device, and also it is our MQTT subscriber. It is also connected to the internet through a network interface, and basically all of the other devices have access to the internet using this one. The other one is virtual machine number 2, that is our MQTT publisher, and it works as a host of SCADA VR. We do have two attacking virtual machines. One of them is going to be as like an internal attacker, the other one external attacker. And we do have a couple of physical components as well. We do have two Raspberry Pis. One of them works as a PLC and sends related packets. The other one works as a access point for a wireless access point for the sensors that we have. We have a camera, we have a flood sensor, we have a couple of other sensors, and we are also able to have like on-site supervision using mobile phones, and these mobile phones are connected to these Raspberry Pi. The important thing here is that we are connected, all of these components are connected together using a network simulator. We use NS3 for that. So basically all of these components, physical or virtual, are connected together using network simulator. So this is another overview of the testbed. You can see like a high-level overview of testbed, how these things are connected. As I said, VM number 1, Ubuntu, is an Ubuntu machine that actually works as a network gateway for us. And we do have two Raspberry Pis, another Ubuntu, and also a attacking virtual machine from inside and outside. So for the emulate attacks that we had in our settings and we collected data on is that we had an attack emulation plan for APT29. So APT29 is a real-world APT group that actually has a lot of attacks throughout the history. So They are very important APT threat actor, and basically because of that, my threat attack framework has its own emulation plan for the APT-29 attacks. So we use that emulation plan, and we use a number of MITRE attack frameworks, TTPs, and we use the MITRE Caldera on Kali number 1, and also on the our virtual machine number 1 to perform these attacks based on what we thought about APT-29. So the emulation plan that we executed contained initial access, reconnaissance, gaining access, lateral movement, persistence, and finally data exfiltration. So this is the process of collecting and labeling the data. So we basically collected two types of data. We collected network data and collected system host logs. So for the network logs, my colleagues talked about how we can use network logs to detect different types of attacks. So I'm not going to go through that in detail. But just can say that we collect the packets with real-time stamps, and we are also collecting host logs. So these host logs are fed into a tool called Spade, and that Spade gives us a provenance graph. So another thing that we have here is the reports of the Caldera that we use to perform the attacks. This report provides us with the attacks metadata and also the process ID of the malicious processes that actually caused the attacks. So using these two resources, we actually can label the data, label the network side of the data, and label the provenance side of the data. So after all of those, we do have a combination of provenance data and the network data that are cleaned and labeled and are there for use as a labeled data set. This is an overview of how this actually looks like, how our dataset looks like. So we did had our experiment in two phases. In fact, the first phase was a 4-day benign activities, just benign. We didn't do any type of attack in this phase. And the next one was a 3-day attack. So we did have a lot of benign packets and benign nodes, provenance nodes, but we also had a lot of attacks that were happening during that phase. So if you can see here that we did have about 46,000 nodes provenance graph for the benign phase and about 53,000 node provenance graph for the phase 2 that is benign. But for the attacks, in total we had about more than 300 attack nodes for the phase 2. That is the sum of all of the other steps that happened during the experiment and during the emulation plan of the attack. These are some of the features that were extracted from the provenance data and provenance graph. So one of the features, for example, is ID. That is basically all of the nodes have those things, and there is the node identifier for nodes. We do have types because we do have a lot of different types of edges or nodes in the provenance graph. We do have a from and to features that are specific for the edges, and they are basically the IDs for the source node and the destination node, and so on. We do have a lot of features that are useful for developing the detection tools. And this is actually how it actually looks like a provenance graph. So here you can see we do have different type of nodes and different type of edges. For example, these are processes, this is an artifact, and these edges are different type of edges that you can see, and that they're generated with different color to show the difference. And this is how actually the complete provenance graph looks like. As I said, it's just for the attack phase 2. So this is basically like a 53,000 node graph, and the blue nodes are actually benign ones, and the reds or with the other colors are those that are attacks. And to compare our dataset with the other dataset available in the literature, you can see that the thing about our dataset is that it is generated on the IoT and IIoT setting. It contains network log and it contains provenance or host logs. So we do also have different phases of an APT. We do have established foothold, collection, data exfiltration, CNC or command and control, persistence, discovery, credential access, lateral movement, and defense evasion. So just going to go through a little bit of how we can use our dataset, how we can use the CIC APT IoT dataset. So as there are a lot of dataset out there that are focusing on the network packets, I'm just going to provide an example on how to use the provenance graph part of the dataset. So as any other data set that you are going to use for machine learning or deep learning tasks, you have to clean the data first, and you have to separate the nodes and edges, because we do have 6 different node type and 4 different edge types. And we do have to like encode some of the features. For example, we do have a feature in the provenance graph that is pass, called pass. It's a pass of the file or pass of the directory, whatever it is. You can encode those things, and you can encode the features. For example, I provided some examples of 3 features here. And then we're gonna have a graph something like this one. So this is like a simple example of how a provenance graph can look like. We do have different type of nodes and different type of edges. So in order to be able to fit that things, so basically, Griffin somehow talked about this, we need to have an embeddings for each of the node in the graphs in order to be able to fit those embeddings into like a downstream machine learning or deep learning task. So for that, and as basically like a baseline method and baseline solution, we use node to wake approach. It works based on the word to wake technique, and it does some random walks on the graph. And it's actually works as, counts the graph as somehow a homogeneous graph. So it's not a very good technique for the provenance graph, but as I said, it's mostly like a baseline method. So it generates some random walks on the provenance graph, and using a script-gram model, it provides some embeddings for each of the node in the graph. And then you can later fit those embeddings into a downstream machine learning task. And this is, let's say, like another one. I actually use this one as for the later task. I use the self-supervised learning-based embeddings instead of node to wake, and compare the results. If you are curious to see how it works, and you can go to our paper on this. So to evaluate how it actually works, then the node to wake method, we used multiple machine learning models, and we used tenfold cross validation. We had 70 to 30 train test split, and I had like 3 different evaluation methods. First was binary classification, basically saying that this node is attack or is benign. Multi-class classification, the model should also say that which subcategory of attacks this node belongs to. And correlated attack stage classification is for be able to actually understand what stage of attack this node belongs to. And the important evaluation metrics for us here is recall and Erfan score. So you can see the results of node to wake embeddings here. This is for the binary classification, and this is for the multi-class classification. You can see the accuracy is pretty high here, but the important metrics for us here is recall and Erfan score. You can see the results here for this table, and this one that is for the multi-class classification. And the final evaluation metric for us is the correlated attack stage classification result. We can see the result for each of the attack stages: collection and exfiltration, CNC and credential access, defense evasion and persistence, and discovery and lateral movement. So this was my presentation on CIC APT IoT dataset. If you have any questions, you can actually type them in the chat, and Sumit will ask them from me. Or if you had any other question, you can email me, and this is my email, and you can contact me using this email, and I'll be more than happy to answer your questions.
Thank you, Irfan, for this insightful presentation. And for all our viewers, if anybody wants to get in touch with Irfan to sort of have more insight on his presentation, his email was just mentioned in the last slide. Irfan, with this, we move on to the Q&A part of today's session. Let me just see if we have any questions in the chat session. So the first question is, Irfan, how did you simulate the low and slow approach in your simulated APT?
That's a very good question. Thank you, Sumit. So the thing, as I mentioned, one of the important characteristics of APTs is that they use a low and slow approach. They're not constantly attacking the targets. They try to remain undetected. So how we did that was that we had a attack emulation plan consisting of more than 30 different techniques, but we didn't execute them one by one, just one after another. So we just had them randomly span through like a 3-day period. So basically, it's not as long as a real APT, but we try to have those approach, and our attacks are like in the case of time, they are distant from each other, and you cannot detect them just by using the time. So that somehow simulates how an actual APT scenario works.
Okay. Thanks for that, Irfan. Our next question is, why are you using recall and F1 score as your main evaluation metrics?
Very good question. That's actually somehow related to the previous question. So as you saw in the slides, the data sets that are related to APTs or advanced persistent threats are highly imbalanced. So you did have like about 53,000 benign nodes, and you had like only 300 attack nodes. So the thing is, when you have a highly imbalanced data set, having an accuracy as your main measurement metric, it can be misleading. So because for whatever machine learning or deep learning model that you develop, you can have more than 99.9% accuracy. So it's not going to be helpful. The important thing for us here is to be able to actually detect those attack points, detect those attack nodes. So that's why we use mostly recall. What recall shows us is how successful we were on detecting those those attack nodes and the graph in the provenance graph. So that's why we use recall, and after that F1 score as our main evaluation metric.
Okay. Thanks for that, Irfan. With this, we move to the next question in today's session. Why did you use a network simulator to connect different components of the test bed? And then the second part of the question is, what were the advantages of this compared to directly connecting them?
So the reason that we use a network simulator, it was NS3, as I mentioned. The reason we use NS3 to connect different components to each other, and we didn't directly connected them to each other, was that we wanted to have a full control over the components and what happens inside our network. So because all of the connections was made through the NS3 and was so that way we had a complete control and complete monitoring capabilities over what happens in our network. So if device 1 sends some packets to device 2, we can easily capture those things because it happens in our simulation, in our own simulation, and it happens in NS3, and using NS3, we can capture all of the packets that we need. So that was the main reason. We could also connect them directly, but we didn't have this extent of control over the packets, over the components, over the network that we had when we are using NS3 for.
Okay. Thanks for that, Irfan. It does certainly, give a good explanation of the question. So with this, we move on to the next question. How do you think that this research can add insight to the cybersecurity of industrial applications?
Thank you. It's also a very great question. So the thing is, as I said, we do have a lack of comprehensive data set that somehow represent this scenario that we were looking for. So we do have do not have enough data set that provides some aspects of like industrial IoTs and also APTs, and these are very important things. So, for example, most of the data sets that are out there are like focusing on different type of attacks, for example, DDoS or DOS, or attacks that are very important when we're dealing with the IoT or industrial IoT. But there are not like too many data sets that would be helpful to detect actual APTs. So what we wanted to show with this data set and we wanted to help was to help the community, help the researchers when they are dealing with APTs, APT scenarios. The other thing that we wanted to somehow influence the literature, influence the community, but with is that how using and how to having the provenance data in the data sets and how to using the provenance data can actually be very helpful in detecting some types of attacks, such as those APT attacks that I was just talking about. We don't have that many data sets that have provenance data and provenance graph in them. So we hope that this data set that we publish somehow helps the researchers that are trying to have the provenance graph, have provenance data, and use those provenance graph and data to detect APTs.
Understood. Thanks, Irfan, for this very clear explanation of this question. With this, we'll move to another question which reflects on what was the motivation behind this particular dataset. So I'll just read the question. What motivated you and your team to create this dataset, and how does this address gaps in existing APT datasets for IIoT?
As I mentioned, because industrial IoTs are being integrated into critical infrastructure, any attack or any disruption in those settings in the industrial IoT can have high impacts. I provided some of the examples, for example, attack on a Ukrainian power plant. And because of that, that's actually very impactful, and that's actually very hard to detect. So what motivated us was that we were trying to prevent those kind of impacts into critical infrastructure in the manufacturing sector, in the energy management sector, in the, I don't know, logistics and transportation sector. We know that anything that happens to an industrial IoT in an IoT setting can be very dangerous for the community, can be very dangerous for the industries. So we are trying to help people to help in this sector, and we're trying to prevent those things. And what was the second part of the question? Sorry.
The second part of the question is, and how does it address the gaps in existing APT datasets for IIoT?
Yeah. So as I said, we do have a lack of the comprehensive dataset. When we were doing this research, we actually didn't have any dataset out there that actually shows, represents the industrial IoT and also represents have provenance data in it. So that actually helps to provide some materials and put that on the gap of this particular gap in the research. That's what I think about.
Thanks for that, Erfan. With this, we'll move on to the next question. As a seasoned, as a seasoned expert, what are the challenges around, creating some of those data sets. Sometimes we have, challenges around, collecting data and then the quality of the data. So this question is sort of, asking those questions. So what challenges did you face in collecting both the provenance and the network logs in a synchronized manner?
Yep. Thank you. So one of the challenges, one of the most important things when you're generating any type of data set is that the data set should be useful. It should be the people in academia and people that are doing research should be able to use that data set. And for that, you need to have your data set as realistic as possible. The data sets that are completely unrealistic and don't have to do anything with the real world scenarios are not going to be that much useful. The other thing is that you should be able, as you mentioned, you should be able to synchronize the collection of provenance graph, provenance data, network logs, host logs, everything. So for that, you need to have full control over the system, over the network, and you need to be able to synchronize this collection of data. That's another challenge. Another thing that I think was very important is what approach you are choosing in order to be able to label the data. So, for example, I didn't mention that because of the lack of time, but actually labeling the provenance graph was very important and was pretty challenging for me because I had to use process IDs and PIDs and PBIDs for that. And with that, I managed to have a solid labeling solution for that. So yeah, that was some of the challenges that I faced with generating the data.
Thank you, Erfan. This was the last question in our today's segment. With this, we come to the end of today's session. I certainly had a good time. I enjoyed, listening to all the presentation. We covered some different topics around IoT and IoT, and we also, covered the malware analysis with respect to the topic. And with this, we will be signing off now. If you're a student, if you're a researcher, or somebody who wants to understand more about the cybersecurity space, the best way to reach out to us is through our LinkedIn channel. So with this, we will be signing off. Thank you for all who have joined us today, and thank you to all our speakers of the day. So thank you.